Hey, this is Ken Risver. We're going to talk about normal distribution, raw scores. Calcium levels in people are normally distributed with a mean of 9.5 milligrams per deciliter and a standard deviation of 0.5 milligrams per deciliter. Individuals with calcium levels in the bottom 15% of the population are considered to have low calcium levels. Find the calcium level that is the borderline between low calcium and those not considered low. Carry your intermediate computations to at least 4 decimal places. Round your answer to at least 1 decimal place. Okay, so the question is, we want to find the borderline between low calcium levels and those not considered low. So somewhere in this normal distribution, which is centered on 9.5 and has a standard deviation of 0.5, which would make this 10 and this 9 and this 8.5 and this 8, 10.5 and 11. Somewhere in here there is a line which, if I drew it vertically, would cut off 15% over here and 85% over there. There's a z-score that does that, and there is a calcium level that does that, because this is not in terms of z yet, right? We haven't standardized this. So there is a calcium level that cuts off 15% of the population. 15% are below that. Our goal here is to find it. Now, how are we going to go about doing that? Well, we know that if we knew what it was, let's just call it x, because that's what it is, we could change it into a z. We would look up that z on a chart, and we would find that z has a value associated with it of 0.1500. So out there exists a x which maps to a z, which maps to 15%. And our goal is to find that x. Well, how are we going to do that? We're going to begin by finding the z. We look up the 15% on the chart, and we can find the z that goes with it. So let's do that. I'm going to go to my my tables, and you can see I actually already marked it off here, but let me erase these other marks. Okay, I know I'm on the left side. I'm on the left table here because we're to the left of the mean. I'm not over here to the right of the mean. And when you look at the chart on the right side here, you can see that all these values are greater than 50%. So we don't want any of those. We want one that is less than 50%, specifically that cuts off 15% of the area. And so I go through these and I look, and I see a 13 here, 15 there. I don't want 15.87, I want less than that. So I look across and I find 15.15 and 14.92. Now, which one am I going to go with? I'm going to go with the one that is closer to 15% exactly. And so that is this one here, 14.92. So looking across, I see the z-score that goes with it is negative 1.00 what? 04. So my answer is negative 1.04 for the z-score. So going back, I've answered this now. Okay, this maps to p of z less than or equal to negative 1.04. Now I want to get that into an x. Well, if it's true that we can change a x using the mean and the standard deviation into a z, it should be true that we can reverse that. And in fact, it is. Because if you take the formula for a z-score, and let me just turn it around so that it still says the same thing. Okay, x minus mu divided by sigma equals z. And I'm going to do some algebra to this. I'm going to multiply both sides by sigma. And when I multiply this whole fraction by sigma, these guys cancel out. And I'm left with x minus mu equals, I'll write it as sigma times z. Okay. The next thing I'm going to do is I'm going to add mu to both sides. And when I add mu to both sides, this negative mu cancels out, and I'm left with x equals mu plus sigma z. And that is a formula that you can use if you know the z value and you know the mean and the standard deviation to find the experimental value, or the population value, or the calcium level in this case that is associated with that z value and that percentage. So what am I going to do now? A little mathematics, simple math. The mean was 9.5, and I'm using this formula. The standard deviation is 0.5. The z-score that is associated with that 15% cutoff is negative 1.04. So multiplying 0.5 times 1.04 gives me 0.52, but because it's negative 1.04, I'm going to end up subtracting 0.52, and my answer would be 8.98. And that's pretty much how you do it. Okay? Let's do another one. The distribution of scores on a standardized aptitude test is approximately normal with a mean of 480. So now, at the center of this distribution is 480. Its standard deviation is 105. So if we count up 105 from there, we would be at 585. And counting down 105, that would make this 375. And I could do that. It's not really necessary. What's important is that we know the mean, we know the standard deviation. What is the minimum score needed to be in the top 25%? Well, the top 25%, let's say, I don't know where it's at. Okay, let's just put a line here and put a 25% there. If I want to find the top 25%, but I'm looking in a chart that shades the left side, should I look up 0.250? No, I shouldn't. I should look up 0.7500 to get this z value. And that's what I'm going to do right now. I'm going to again go to the table, and I'm now working on the left side or the right side, and in there I'm going to try to find 0.7500. So I'm way up here. I'm in the 0.6 row, and I'm looking across, and I see 0.7486 and 0.7517. I think 0.7486 is closer, so therefore I go with that one, which is 0.67 is my z-score. So going back to where I was at, I will again use the formula, which was that x equals mu plus sigma z. And I put in 480 because that's my mean. I put in sigma next. What's sigma? It's 105. And I put in 0.67, which is approximately 2/3. So if I think what's 2/3 of that, it's 70. And if I go 480 plus 70, I get my answer is 550. And that is what I would put into Alex. Let's check if Alex is still alive down here. I'm going to put in 550. Oh, but okay, it logged me out. So I'm going to save that for the next video. I'm going to show you how to do it in Alex. But I think you get it. I'm going to stop there. Bye-bye.